Notice when it comes to periodic table, there are certain patterns that we need to identify. One of them is being diagonal relationship. The second period elements and the third period elements, right, which are diagonally aligned to each other, will always have similar properties. Got it? For example, if you take second period elements, that includes lithium, beryllium, boron, carbon, nitrogen, oxygen. As it comes to third period elements, that would be sodium, magnesium, right, aluminum, silicon, phosphorus, sulfur. Okay. Now, what has been noticed is that lithium and magnesium would have very similar properties. Beryllium and aluminum will have similar properties. Boron and silicon will have similar properties. Same goes with carbon and phosphorus, and same goes with nitrogen and sulfur. Okay, these are the elements which do show similar properties. Got it? Now, why would that show? Because of the ionic potential. Ionic potential. What is ionic potential means? The potential factor of these elements depends upon how much charge they carry upon what is the radius of the atom. If this factor is seen very close by for the elements, they start showing similar properties. Okay. So if it comes to lithium plus and magnesium 2 plus, they have almost similar properties. Got it? I mean, they will have similar ionic potential form. Okay. Now the same goes with uh, rest of the elements here. Here, everybody, right? Just for the sake of example, let me write down here. The radius of Mg2 plus, correct, is 72 picometer, while radius of lithium plus is around 76 picometer. So you could notice that they are very, very comparable form. Okay. That's the reason why you will notice this kind of idea. Okay. Same goes with beryllium also. Okay. So when it comes to beryllium, you would have almost similar size to that of aluminum here. Got it? Next, what are typical elements here? So if it comes to typical elements, we could say that uh, third period elements, except the inert gas, they are called as typical elements. Okay. Why that happens is in most of the compounds, they represent the properties of these. They represent these elements would be the first one to represent all the properties of those compounds. Okay, that's why they are called as typical elements. Examples, if you notice, that starts from sodium, magnesium, aluminum, silicon, phosphorus, sulfur, and chlorine. These are typical elements, right? Next, representative elements. In fact, all S and P elements, all S and P elements which have an incomplete octet, that means the valence shell electron should be less than 8. Those are called as representative elements. See, every element in S and P except the inert gases, these are all called as representative elements. Got it? And next, when it comes to man-made element, it is technetium. Okay, technetium, that is the first one which was made. And man-made lanthanum is promethium, PM. Got it? Now, coming to the other important terms are metals, non-metals, and metalloids. Most of the elements are metal in the periodic table. and usually they are solid state at room temperature except for mercury and gallium. Gallium's melting point is only 31 degrees. Mercury is even low, correct? It is around 5 degrees. Next, high boiling point and high melting point is observed in the case of metals, except for gallium and mercury, which has a low melting point. Of course, they will have boiling point higher, but the melting point lower. Got it? And metals are highly heat and electrical conductors. That means they are very good conductors of heat and electricity. Okay. Metals are generally malleable and ductile. Okay, ductile as in we can convert that into sheets. Ductile as in we can convert that into sheets, and malleable as in we can convert into sheets, and ductile as in we can convert into ducts of long length chains. Okay. While when it comes to non-metals, usually they are solids or gases, and they have low boiling point and melting point, except carbon and boron. Okay, they are generally brittle. They have less malleable and ductile nature. Okay. Now, when it comes to metalloids, both metals and non-metal characters are being observed in this case. That includes silicon, germanium, arsenic, antimony, tellurium, and polonium. Got it? So this is a very simple briefing that you need to know. I'm sure you have been learning this right from school. Okay. Next, when it comes to IUPAC nomenclature for elements above 100, see what happened. Up to certain number of elements which were discovered, right? They were named after the scientist who has discovered, or based on the property of the element, the name was given. But after 100, they decided to follow a nomenclature. IUPAC has decided to follow a nomenclature. In that nomenclature, they gave something called a root name for every number. And based on that, the suffix of every number has to end with em, IUM. For example, if you notice 0, 1, 2, 3, 4, and so on, it starts with nil, un, bi, tri, quad, pent, hex, sept, not hept, it is sept, oct, and n. So these two are slightly different from organic representations. In organic, 7 means hept, 9 means non. But unlike that, here 7 is sept and 9 is n. Okay. Using that, if you figure out what is the name, IUPAC name, and what is the official name that was given to it, this is the IUPAC representation. But based on which scientist has discovered, they have usually given their names. Check out. 101 is basically un, and there is nil, and there is un again, and em. So that would be the name. Un nil em. In un nil un em. Okay. So what is the symbol used for it is UNU. Okay. And the official name given was, Mendelevium. 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 The official symbol is MD. 102 is now Un Nil Bium. Unil Bium. UNB. And official name is Nobelium. Correct? Nobelium, which is NO. 103 is Un Nil Trium. Okay, Un Nil Trium. UNT, and that is Lawrencium. That is Lawrencium. Got it? Which is LR. And 104 is Nil Quadium. Nil Quadium, UNQ. Got it? The name is Rutherfordium. Official name is Rutherfordium,
So,
RF. Yes, Vito.
so did Rutherford discover this element, or it was just named after him?
No, it was named after him. Okay. Usually, those days, if there was anything man made by lab or synthesized by lab, they used to give it on the name of a particular Nobel winner scientist. Okay, clear. So it's not particularly he invented it or he discovered. Okay, next 105 is un nil pentium. Pentium. So you can see UNP. Okay, this was known as dubnium. Got it? DB. 106 was un nil hexium. Un nil hexium, which is UNH, and the official name was Seborgium. Seborgium. SG. Seborgium is SG. 107 is un nil octium. Un nil octium. Got it? UN O. Sorry, this is 7, right? My mistake. Un nil septium. Un nil septium. UNS. Got it? So this was borium, named after Bohr. Then this was un nil octium, which is UNO, and this is hazium. This was hazium, which is HS. And 109 was un nil enium. Very important here. So this is what usually confuses us. This is un nil enium, and which is UUN. Got it? UN and UNE. UNE. Okay. So this is metnanium, which is empty. And lastly, this is un nilium. Un nilium. So UUN. Okay. This is Darmstadtium. Darmstadtium, which is DT. Clear? I hope all of you got this. So this is one simple area I think that you should learn how to write them. Okay, please check it out. Of course, it will take some time and practice to remember all these names. Nevertheless, if you start writing once or twice, you will get a habit of it. Okay. Let's see, next one. What are those parameters which have the various trends over periodic table? The first thing we need to learn is effective nuclear charge. What do you mean by effective nuclear charge? See, if this is a nucleus and around the nucleus there are various electrons, and then there is some outermost electrons also. There are some outermost electrons also. That way, if you notice, let's say this is the outermost electron present in it. Okay. So if this is the outermost electron, then these valence electron, which is the outermost electron, correct, that would experience lesser of an attraction from nucleus due to the intervening electrons in between them, right? Like this. These two are supposed to attract, but there are certain electrons that comes in between them, because of which those electrons will repel the outermost electron and those will attract the nucleus, because of which the effective amount of attraction that's supposed to happen to the outermost electron does not take place, and it in fact decreases. So lesser the attraction is observed from the nucleus due to the intervening of the inner electrons, right? So what is happening is nucleus getting shielded by the inner electrons. Now see, the shielding of nucleus by the inner electron is what we term as shielding effect. We call it as shielding effect. Okay. The other terminology used is screening effect, shielding effect or screening effect. Okay. Now, if you want to figure out what is the net charge that electron actually carries on the outermost orbit, that Z effective will be equal to atomic number minus sigma. Atomic number is the actual total nuclear charge which is expected, right? But sigma represent the amount of loss of the attraction due to the intervening electrons. So that is called as screening factor constant or screening constant, right? So Z effective is the effective nuclear charge which is experienced by the electron. Z is the total nuclear charge minus sigma is the screening factor. To figure out mathematically, there are something called Slater's rule which explains us easily to calculate. What Slater's rule suggests that if Ns and Np electrons contribute a screening factor of 0.35, which means if there are any electrons present, for example, let me show you this way. Suppose if this is a nucleus and this is the outermost orbit and this is the electron on which you are trying to figure out what is the amount of Z effective observed. But within this orbit, there might be other electrons also. So those electrons will also contribute to some amount of repulsion. Okay. How much amount of repulsion they are giving? Per electron, they will give you 0.35 detection. 0.35 amount of repulsion, or we can say this as detection of charge which is coming from the nucleus. Got it? So 0.35 of every electron is contributing as a repulsive factor. If you have n minus 1 shell, which is slightly inner shell, those inner shell will contribute more. So the electrons present in the inner shell will contribute a factor of 0.85 units. So 0.85 units of repulsion they will carry. And if you go towards n minus 2, n minus 3, and n minus 4, and so on, all the inner shells will contribute a factor of at least 1. And if you are on 1s electron, 1s orbit, that means there is no other orbit or no other electron you are worried about. You're only worried about the 1s, the first orbit. In that case, the repulsive contribution is around 0.3 units. Okay, so these are screening factor units, per electron here. Okay, let me show you one by one in simple terms how do we calculate this with an example. Okay, so first let me start with as simple as lithium. Got it? For example, if you start with lithium has total of 3 electrons, so which is 1s2 and 2s1. So the outermost electron is 2s only. The outermost electron is 2s. So if it is only 2s, then how much will be the value here? So that will be, since this is the outermost orbit, the inner electrons will contribute to a factor, n minus 1 will contribute to a factor of 0.85. So therefore, the sigma value will be equal to, there are two electrons, each contributing 0.85. So which is 1.7. That means the Z effective on the last electron in the lithium will experience 3 minus 1.7, only 1.3 units of nuclear charge. Nuclear charge is expected on the last electron. Everybody understood? Let me show you about the next element, sodium. Sodium's configuration is 1s2, 2s2, 2p6, and 3s1. So you can see this is the last electron. In the last shell, we do not have any other electron other than 3s1. And therefore, now sigma will be equal to You can see these are n minus 1 electrons. So there are 8 of them. So 8 into 0.85. And next, these two are n minus 2 orbit electrons. So they contribute 1 unit to it, correct? So 8 into 0.85 plus 2.1. So this is 6.8 plus 2, which is 8.8. So the Z effective value for sodium is 11 minus 8.8. So that is 2.2. So this will be 2 points. Check out same for sodium. Sodium is 19. So that would be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Now, this is the outermost electron here. So how much will be the contributing factor? You see, these are n minus 1. So n minus 1 is 8 electrons. Each contribute 0.85 of repulsion. And rest all are n minus 2 and n minus 3. Hence, that will contribute a total of 10 electrons into 1. Okay, so that is 6.8 plus 10, so which is 16.8. So Z effective will be equal to 19 minus 16.8. 19 minus 16.8, which is again coming out to be 2.2. Got it? You would notice there is a pattern that is observed as you are going down the group. Except for lithium, if you calculate it for sodium, potassium, rubidium, cesium, francium, all of them have one particular pattern. The pattern is their Z effective remains constant. That means the last electron will only experience the same amount of Z effective. Now tell me, if the Z effective, that means the last electron is not getting strongly attracted to the nucleus, but the shells are increasing. So as the new shells are being added, because lithium will have 2s1, sodium will have 3s1, potassium will have 4s1, and so on, the number of shells are increasing. Hence, we can say that since Z effective is constant and the number of shells are increasing, the size of the atom automatically increases. In fact, it increases drastically. So that is the important note to be learned here. That is, okay, down the group, down the group, Z effective remains constant, remains same, almost same for every group elements, every group element. Okay, since electron are added, since electrons are added to new shells, size of the atom, right? Size of the atom increases. Size of the atom increases. I hope you understood the conclusion for screening factors calculation from top to bottom, that is down the group. Any doubt here? And you might ask, sir, is this works only on S block? No, it works on all the groups. Whether you take S block, group 1, group 2, P block, 13, 14, 15, 16, everywhere the size of the atom as you go down the group usually increases. Of course, there are exceptions, but in most cases, size of the atom will always increase. Do you have any doubt?
No, sir.
Kapil, Manav?
No doubt, sir.
No doubt.
Right. Now, let's talk about how it goes from left to right. Okay. So, from left to right in the periodic table. If you go from left to right, the elements that we should be concerned about is right from beryllium. So, beryllium 4 is 1s2 and 2s2. So what I'll do, I'll put it like this: 2s2, 1s2, 2s1, and 2s1, just to showcase one of them is a reference electron on which we are calculating the Z effective. So on this reference electron, how much will be the sigma value here? Sigma would be equal to, you can see, one electron will contribute around 0.35 units, because same shell, right? 2s is in same shell as that of this outermost electron, and two electrons in n minus 1, and n minus 1 contributes 0.85. Now this is coming out to be 2.05. So therefore the Z effective value will be equal to 4 minus 2.05, which is 1.95. So 1.95 is the Z effective value. All right. And next, when it comes to boron, for boron we have 1s2, 2s2, and 2p1. Okay. So now this will become the outermost orbit. So in that case, what will be the sigma value? Sigma value will be equal to, this is from the same shell. So 2 into 0.35 plus 2 into 0.85. Got it? And that's coming out to be approximately 2.4 units. So Z effective will be equal to 5 minus 2.4. Okay. So that is coming out to be 2.6. And when it comes to carbon, you'll see carbon 6, which is 1s2, 2s2, 2p1, and 2p1. I'll write it this way just to show the reference. So again, I will have sigma is equal to 1 into, 3 into 0.35 plus 2 into 0.85. Okay. So that is 1.7 plus 1.05. Clear? So that is coming out to be 2.75. So Z effective will be equal to 6 minus 2.75. Got it? So how much we are getting here? 3.25 is what you are getting. Correct? Now please understand one thing. If it starts from lithium onwards, lithium towards beryllium, towards boron, towards carbon, and so on and so on. If we check out the sigma value is actually increasing. So Z effective in sigma value here is 1.7. It was originally 1.7. I mean, for lithium it is 1.7. For beryllium it is 1.95. For boron it was 2.4. Now here it is 2.75. Now based on that, what is happening to the Z effective value here? Check out Z effective value. Z effective value here in the first case was 1.3. So 1.3 for beryllium, it is 1. For beryllium, sorry, Z effective was 2.05. My mistake. This was 2.05, and Z effective is 1.95, and boron it is 2.6, carbon it is 3.25. What did you notice out of these four calculations? Check properly. This helps us realize that left to right in a periodic table, left to right in a particular period, both sigma value and Z effective value, both of them are increasing. Okay. Significantly, Z effective is increasing. So that is what will account for its smaller size of the atom. So left to right, what happens to the size now? Because the Z effective is increasing, that means the electron would be strongly attracted to the nucleus, which makes it to start shrinking. So the size will become smaller and smaller. Got it? So this is the next note we need to understand. That is from left to right. From left to right. From left to right, both sigma and Z effective are increasing. Increasing. Suggesting suggesting electrons added to the electrons added to same shell, same shell decreases size of the atom. So please notice this case. Let me know if you have any doubt how it goes from left to right. Okay, a general graph, if you see how the size varies with respect to various elements. Check here. If lithium is here, correct, all the way beryllium decreases towards this end, then it decreases towards boron, decreases towards carbon, sorry, slight decreases towards carbon, again decreases towards nitrogen, then to oxygen, and then to fluorine. So fluorine has very small size. So fluorine, oxygen, nitrogen, carbon, boron, beryllium, and lithium. This is the radius versus Z. While when it comes to size here, lithium is here, sodium is here, potassium is even further, and then rubidium here, cesium here. So this will be cesium, rubidium, potassium, sodium, lithium. A similar trend is observed even when it comes to fluorine. So fluorine is here, then calcium, then chlorine, then bromine, then iodine. So this is iodine, bromine, chlorine, and fluorine. This is how the size has been observed. Right. So this is again radius versus Z value. So it's pretty much clear that left to right how the size is varying and down the group how the size is varying. Okay. Now what if some random element is given and I need to find out what is the Z effective in it? Let's try doing that. Let us take the case of iron. Iron 26. So in this case, if you write the configuration, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. This is how we write, correct? But for writing, for identification of the uh, Z effective, we need to write the elements of the same period, same shell on the same direction. 4s1, 3d6, sorry. So 3d6, and lastly we'll have 4s1 and 4s1. This is how I write it down so that I can figure out what will be the Z effective on the last electron. Now you can see this is nth shell, this is n minus 1th shell, this is n minus 2 shell, and the number of electrons present in it. Okay. So now notice how do we calculate the sigma value? Sigma will be equal to 1 electron, which is 0.25, plus there are total of 14 electrons contributing 0.85, plus 10 into 1 electron, which is 22. That is the value which you will get. So that is coming out to be around 22.25. Okay. So you can see Z effective value in this case for 4s1 electron is found to be 26 minus 22.25, which is coming out to be 3.75. So you can see which is very similar to that of carbon. Okay. This is the Z effective observed on the last electron here. Please check everyone if you have understood this or no.
Sir, in every case, we have to divide the last one, like 4s2 into 4s1 and 4s1.
Every time you have the last shell electron, you divide into 2 because you are referring to one electron as the last electron on which you are calculating. Okay.
So how to do it if it is anything apart from S, if it is P or D?
P or D. Okay, we'll do that also. Okay. So how do we calculate that Z effective? We'll see now. One second. See, suppose if you have same thing, but this time I'm writing it as for Fe plus 2. Fe plus 2. Fe plus 2 configuration will be the 4s2 electrons are completely gone. So what do we have here? So we'll have this as 1s2, and then we have 2s2, 2p6, correct? So then we have 3s2, 3p6, and then we have 3d, then we have 3d5 and 3d1. I'm putting it separately because total we have 3d6 here. So I'm writing it as 3d5 and 3d1 here. Got it? And now
Yes, sir.
notice any yes, beta, any doubt?
No, no, sir, continue.
Right. So now notice this one. When it comes to 3D, you don't join with this 3D5 here because the inner D will have a different point of view than S and P. So now what is the contribution factor here? Will be sigma, which is equal to 5d electrons, each contributing 0.35 because it's in the same shell. But now it says, sir, ये भी तो same shell है. But when you are calculating it for d electrons, right? D will contribute. Rest all which is lower than that, right? Anything which is lower than that, they all will contribute at least 1 unit. So how much we have? Check out. This is 8 plus 8 plus 2. So all of these will contribute one electron differential part. So therefore, we will have 5 into 0.35, which is 1.75, and this will be 18, which makes it 19.75. So what will be the Z effective beta? Z effective will be equal to Z minus sigma. Z minus sigma. Z minus sigma is how much? So Z is 26 minus 19.75. Correct? And what is happening to the Z effective now? So I can say this will become 6.25. What have you noticed, beta? You have noticed that the Z effective is actually increasing the minute you start making it as a positive value. Okay, here there are two important notes that to be made. One is that for nth d valence electron n minus 1 spd contributes, sorry, n minus 1 and below, n minus 1 and below contributes sigma value of 1 unit. Correct? So all of them will contribute 1 unit here. This brings to the other conclusion that, note this down here, note that, okay? Note that as positive charge increases, positive charge increases, correct? Z effective value increases, and if Z effective increases, size decreases. Correct? I think this factor is clear. Please check this too now. Dev, did you understand how to calculate now?
Yes, sir. Sir,
Yes, beta.
But the positive charge indicates that the electrons have gone out, right?
They have completely ionized from the atom. They are not a part of atom anymore.
So that means the size should increase.
The outermost electrons have been removed. Correct. So if outermost electron is gone, now what is happening? The overall charge of the species is positive, which suggests that the nuclear charge on every other electron will start increasing now. Got it? So listen, it is like this. If you have more number of electrons, the nucleus has to share its positive charge with almost all the electrons. If you have less number of electrons, it has to share with only less number of electrons. Correct? So the Z effective will be higher. Okay. And the converse is also true. That means if you keep adding the electrons, the Z effective will be becoming smaller and lesser, and the size of the atom will become larger. Okay. Any doubt? Right. Now see the next factor. There are four types of radius which will come across. Okay. Now, what do you mean by types of radius? Isn't it one radius for everything? No. For example, let me show you. Let me tell you. When it comes to hydrogen atom, you will not find in nature only as atom, right? You find it as molecule. So hydrogen's existence is either in the form of H2, which is in a gaseous form, or sodium hydride, which is in an ionic form. Okay, where it is basically hydrogen has a complete positive charge, sorry, negative charge, and sodium has complete positive charge. Or we can also have other forms, something like HCl, where hydrogen has positive charge, chlorine has negative charge. So have you noticed that hydrogen in all different forms exists in different ways? Some cases when it is H2, here it is completely existing with zero charge. In sodium, it is existing completely with negative charge. With HCl, it is existing with partial positive charge. So, if the same element having different types of charges on it, right? It may be full charge or a partial charge and so on. It will affect its size. Okay, it will affect the size. That's why, in a broad way, we classified the size of elements into four types. One, a covalent radius, when it is making a covalent bond with the same atom. Correct? Within that covalent radius, we have two kinds. One is homonuclear or heteronuclear, which means between the two same atoms or two different atoms. Got it? Hydrogen with hydrogen, that is H2, that is homonuclear. Hydrogen with HCl, that is heteronuclear. So in these two also there is a variation in the size. But this variation of a size at a broad way is called as covalent radius. This is covalent radius. Then we have ionic radius. Ionic radius is when you have complete charge, either complete positive charge or complete negative charge. H plus ion. H plus ion is an ionic radius. H minus ion is an ionic radius. Okay. And within that, a cation will have a different radius, anion will have a different radius. Correct? Then we have something called metallic radius. Of course, it is not applicable for hydrogen, but all the metals will have metallic radius. That means when they are attached with the other metal atoms, correct? In that case, what is the radius they are having? That is called metallic radius. And last one is a van der Waal radius. Van der Waal radius is between two molecules. It is not between the atoms. Generally, it is between molecules. Between the two molecules, what is the size each molecule will have? And we average out that size per atom. Okay. And that is what we call it as van der Waal radius. So have you understood that every atom, right? Atoms may have multiple radii. It might have a covalent form, ionic form, van der Waals form, or a metallic form. Okay, broad way, these are the four types of radius we have to define. So now let me start with the covalent radius. So covalent radius is defined such a way that it is one half of the distance between the nucleus. Okay, one half of the distance between the nucleus where atoms are covalently bonded. The covalent bond must be a single bond here. So we are talking about a single bond here. For instance, if I'm talking about, let's say, two atoms here like this one, and the next atom, which is of same size, and this is how the overlap is happening here, correct? And the distance between the nucleus here, this is, let's say, the distance between the two centers here. So this is the total distance between two nucleus. So the distance between the two nucleus, everybody, is called as internuclear distance. Easy to remember, IND, right? So in that case, the covalent radius of the element here, both of them are X elements, by the way. X means same atom. This is homonuclear covalent radius. Correct. So in that case, RC covalent radius will be equal to half of IND internuclear distance. Okay. For example, okay, if you notice Cl2 has IND internuclear distance as 198 picometer. Okay, while we say the covalent radius is equal to 198 by 2, which is 99 picometers. So 99 picometer is the radius of fluorine. Done. This is about covalent radius. I hope you guys understood that. Yeah, any doubt? Please check. None? Okay. Few data which I can help you. Of course, this is not something you need to mug up, but just for the reference, while you are solving questions, you might come across. So you can see covalent radius. I'm writing about covalent radius of RC, covalent radius of hydrogen. Covalent radius of hydrogen is 32 picometers. Right? Is 32 picometers. Clear? Covalent radius of sodium, when sodium is making some covalent bonds, in that case, how much it will be? It is 155 picometers. 155 picometers. Clear? And covalent radius of potassium is 198 picometers. And on the other hand, if you see the smallest one here, correct, out of all the elements, which is smallest one. Now see the difference here. When the size of an atom, we say fluorine is the smallest size, because if you go from left to right, it is smaller in size. Correct. But when it comes to covalent radius, you'll see hydrogen is the smallest one. Got it? Because if it comes to uh, fluorine here, sorry, covalent radius of fluorine. So covalent radius of fluorine is 64, right? 64 picometers. Done. Now let's come to understanding of heterodiatomic species. If it is heterodiatomic species, which means we have two different atoms. In that case, how does the size get influenced? Okay, so check out. In this case, suppose if I take the same element this time, correct? Here, this way. And let's say the size of the other one is not exactly same. The size of this nucleus is slightly different. Let's say this is how the size is. Like this. Okay. And this is the internuclear distance between these two. So let's say this is A and or X and Y here. Okay. X and Y here. So this is the internuclear distance. Now, simply can we take the average of two? Answer is no. That is not how we calculate. See, if we have, let's say I'll take this as A and B, then the internuclear distance between A and B, which is IND in this case, actually depends upon the properties like what is the uh, electronegative difference between these two. Therefore, it is RA plus RB minus 0.09 into delta X, right? So this formula is called as Stevenson-Shoemaker formula, which basically helps us calculate what is the distance between two covalently bonded heteronuclear atoms. Okay, but all you need to know is electronegative difference. So this X is electronegative difference, clear? And RA and RB are in picometers in this case. While calculating, it should be in picometers. Okay, electronegative difference in Pauling scale. We'll learn going ahead what is Pauling scale, but that is what you will need to figure out. Any doubt here, beta? Please check. This is how you calculate the heteronuclear form. Done?
Sir, in
Suppose.
this, the line is joining exactly the center of both the atoms, right?
Yes, beta. Center of both the atoms. Got it? Sorry, these are not in picometer. My mistake. It is in Armstrongs. Sorry, picometers, that will become 9. Okay. See, let me show you with the calculation actually, then that will be better. Correct. So let me calculate and show you how much difference that it comes. See, the absolute covalent radius of carbon. Let me show you with an example. Correct. Carbon is 0.77 Armstrongs. 77 Armstrongs. Or if you write it in picometer, it is 77 picometers. And radius, covalent radius of fluorine. Okay, for fluorine, it is 0.64 Armstrongs or 64 picometer. I just wrote it down. Electronegativity of carbon is 2.55, whereas electronegativity of fluorine is very close to 4 or exact value is 3.98. Okay. Now, if you calculate just the average or radii or the internuclear distance alone, if I calculate just the internuclear distance alone, then what is the value you will get? RC plus RF, correct? But that is not true. This is not exactly internuclear distance. But how much is this value here? That is 0.77 plus 0.64, right? So that comes to be 1.41 Armstrongs. While if you calculate the internuclear distance, let's say D of C and F distance I'm calculating. So what is the formula I'll get? Radius of carbon plus radius of fluorine minus 0.09 into electronegative difference. So that makes it 0.77 plus 0.64 minus 0.09 into electronegative difference. How much is the electronegative difference here? Correct. So the difference is 1.43. 3.98 minus 2.55. Now, on calculating all of this value, correct. So sum of this and that is 1.41 minus all of this, that is coming out to be 1.2813. 1.2813. Got it? So this is the actual distance. This is the actual distance. Got it? Any doubt here? Now, how much is of reduction has happened? Size reduction due to electronegative difference is how much? 0.12 Armstrongs. So that is the value that you will get after multiplying this entire thing. You multiply these three, you will get this as 0.12 Armstrongs. Okay. See, what does this mean? Have you noticed something? More the electronegative difference between the atoms, smaller their size will start becoming. Both of them will start getting reduced. And closer they'll start coming. Bond length decreases. Okay. So let me put that into conclusion. See the note here. The note here is, as electronegative difference between atom AB increases, size of atoms decreases, bond length or internuclear distance decreases. That's the important factor to learn from Shoemaker formula. Clear, guys? Right. Now let's understand metallic radius. Metal atoms which are closely packed in metallic crystal, they will be giving out metallic radius. That means they are tightly packed with one another. So in simple term, we can understand is as if, because they do not have any charge, as if these two atoms are so tightly packed that they almost touch each other. That's it. If they are touching each other, we can expect that the internuclear distance between them, right? So this will be the internuclear distance here, IND. This is element X, this is element X for same element. So radius of the crystal or metallic radius is simply internuclear distance by 2. That's it. That will be the metallic radius. Nothing much to discuss. This is how much you will get. Next is van der Waal radius. Van der Waal radius is between the nucleus. For example, if I take the same diagram here, suppose if at all I take this diagram here, and let's say I take the other diagram here like this, correct? Now, what I can say, between these two, the most closest distance is this one. Let's say this is how close the molecule can come. Van der Waal attraction implies that there is an attraction between the molecules. Between the molecules, if there is any attraction, atoms can come close by, but they cannot overlap with each other. They come to this distance almost. So, if I particularly figure out, let's say this distance between this point to this point here, this point to this point here, this is how much the distance that they can create, closest distance which they can create. Now this becomes intermolecular distance, IMD, intermolecular distance. Okay. So if let's say this is element X and X and this is X and X. So between the X and X of two different molecules, that is intermolecular distance. Okay. Now, if I calculate the radius of the van der Waal radius here, RV will be equal to intermolecular distance by 2. Okay. So now, if you naturally compare for a particular element, if an element possesses van der Waal radius, if it possesses metallic radius, and if it possesses some kind of a covalent radius, I can clearly notice that based on the amount of overlap what we are getting, we can say that van der Waal radius is definitely larger compared to metallic radius compared to covalent radius. Okay. Now notice in non-metals, when the atoms are coming close to each other in a solid state, these molecules have certain defined intermolecular distances, and that is this distance. This is the closest distance that they can come across. And what has been approximately noticed is that van der Waal radius is almost 40% larger than the uh, covalent radius, and metallic radius is 15% larger than the covalent radius for a particular element, any element if you take it. So these are the respective values of covalent radius and van der Waal radius. You can check it out. So hydrogen is 0.37. So these are all in Armstrong units. As I have written it here, sorry. I have written it here. These are all in Armstrong units. Please check. So all of these elements have higher van der Waal radius than covalent radius. Done. Next. When you are comparing radius from left to right, compare only that type of radius which defines the properties of the element. Now, this is very important because while taking an exam, which kind of radius should we prefer? Because hydrogen, should I consider it as 0.37 Armstrongs or should I consider it as 1.2 Armstrongs? Now, my suggestion is we should take 0.37 Armstrongs. Why? Because most of the hydrogen atoms would exist in the covalent forms, whether it is in H2, HCl, HF, right? In any other H2SO4, HCN, or any hydrocarbon, C2H4, everywhere there is hydrogen, it has mainly covalent radius. So the most frequent form of radius which you observe for hydrogen is covalent radius. So that's the one which you will use whenever you're comparing with the other elements. Similarly, when it comes to lithium, lithium hardly makes any covalent compounds. It mainly makes complete ionic compounds. So therefore, you will only consider the ionic radius in this case. Okay, sorry, metallic radius. So that means you consider only metallic radius. So for metals, we generally consider metallic radius. For all of this, boron, coke, carbon, nitrogen, oxygen, fluorine, we consider covalent radius. Now, interestingly, when it comes to neon, right? Neon is an inert gas element. It does not show any covalent bonds with anybody, correct? Neither it shows any kind of a metallic features. So the only radius that we will compare is van der Waal radius. We'll compare only van der Waal radius, everybody. Clear? So have you noticed something? Left to right, there is a trend. Check properly. The size is decreasing and becoming minimum towards fluorine, but as it comes to the neon, it is increasing again. So that's why we say left to right, the size is decreasing. But up to which group? Up to 17 group. Suddenly it starts increasing towards group 18. Because for group 18, we only have van der Waal radius to be considered. This factor is clear, everybody? Dev, Kapil, any doubt here? Manav?
Yes, I had one doubt.
Yes, beta.
Um, for covalent radius and metallic radius as well, both the atoms need to be of the same size exactly.
No. Covalent radius, see, atom's size, you cannot identify unless it is completely isolated, correct? Now, if I ask you, क्लोरीन का साइज कितना है, क्लोरीन एटम का साइज कितना है, क्लोरीन एटम का तो आप नहीं बता सकते हो ना, बिकॉज क्लोरीन एटॉमिक फॉर्म में नहीं मिलता है, राइट?
Right.
सो दैट मीन्स क्लोरीन को आप मेजर करोगे या तो HCl में, या Cl2 में, या NaCl में, बराबर?
Yeah.
Now, if you calculate in NaCl, it is completely ionic radius. If you calculate in HCl, it is covalent radius, but heteroatomic. If you calculate that in Cl2, it is covalent radius, isn't it? So the perspective of the chlorine size is changing every time you go with a different molecule, isn't it? So that's why when it comes to chlorine molecule, Cl2 itself has two types of radius. One is a covalent radius, the other one is a van der Waal radius. That means between two chlorine atoms, if I average the size of chlorine, I will get a new size of chlorine. So there are two types of radius chlorine majorly have. One is covalent, the other one is van der Waal. Okay. That's the reason why you will see chlorine has these two radiuses here. One is 99, which you got as the chlorine size, which is the covalent radius. Correct. The other one is 174, which is the van der Waal radius. They have clear, beta?
Yes, sir.
Right. Yeah. Right. Next, check out. When it comes to shielding effect of subshells, we learned this in structure of atom that the s orbitals would have more electron densities closer to the nucleus. So Ns will have more screening effect, which means it has more closeness to the nucleus, so it can shield better. It can shield the outermost electrons better. Correct. So therefore, Ns will have more shielding effect or more shielding factor. Np will have the next one, Nd and Nf. So as you go towards the f orbitals, the shielding nature will be weaker. Let me show you pictorially. What does that mean? For example, if this is nucleus, and s orbitals are usually present across every point. So suppose if I take an electron here at one time, the outermost electron is once moving here, once it is moving here, once it is moving here and here and here. See, at every point of time, at every point, you will notice that there is a strong screening from s electrons. That means strong repulsion, or it is shielding the nucleus. Okay. But what if you have p orbital? See, when it comes to p orbital is basically more like this, correct? Like a dumbbell shape here, this one. Okay. Now notice when the electron is here, it is best shielding. But when the electron is here, now the shielding factor is less. When the electron is here, the shielding factor is less. When it is here, it is best shielding again. When it is here, it is hardly shielding. It is directly getting in contact with the nucleus. When it is here, it is slightly less shielding. Correct? So this way, p orbital will not shield greatly from all the directions, unlike s orbital. Now, when it comes to d orbitals are even worse because they are more sharper orbitals with a dumbbell shape like this. This is d orbital. So now, this will be hardly shielded. This electron will be hardly shielded. This electron also will be hardly shielded. Only this electron will be shielded. This electron will be hardly shielded. Only this electron will be shielded. Correct? So you can see that's the reason why as you see s orbital, it will have a better shielding of electrons compared to T, D and F. Okay. So this can be directly correlated to its penetrating power. More the penetrating power, more is the shielding effect. More shielding effect means strongly it is shielding so that the outermost electron will not observe and will not attract the nucleus strongly. Okay. So you can see ability to be closer to the nucleus is called the penetrating power, and Ns, Np, Nd, Nf is the correct way. Okay. And next, see, if the Z effective increases cation and Z effective for the anion, Z effective always increases for cations, Z effective decreases for anions. And this I told you already. So if the Z effective considered, N plus will have N is any element N, okay? N plus will have more Z effective compared to N minus. Okay. If you have any isoelectronic species means they have same number of electrons. Like H minus has 2 electrons, lithium has 2 electrons, beryllium has 2 electrons, boron plus 3 has 2 electrons. Okay. In such case, Since this has two electrons here, the Z effective is more here because it has positive charge. Then beryllium, then lithium, then H minus. And that's why Z effective, if you compare, this is how it varies. And you know that Z effective usually always be inversely proportional to the size. So Z effective is inversely proportional to the size of the ion or the covalent form. Therefore, if it comes to size here, definitely we can say that N3 minus will have a larger size, then O2 minus, then F minus, then Na plus, then Mg2 plus, then Al plus 3. All of this will have the smaller size. Got it? Now, let's focus on some exceptions here. For example, group 13. In the case of group 13, we expect that down the group there should be an increase in the size. That is boron to aluminum, gallium, indium, and thallium. But actually, what has been noticed is that aluminum slightly overpowers gallium, and in fact, it has a larger size than gallium. While indium and thallium also has very similar case, thallium leading by a small margin, but yet they are very close to each other. Okay. Now notice boron, aluminum, gallium, indium, thallium. If you compare, Z effective is actually increasing towards thallium. So 2.6, 3.5, 5, 5, and 5.6. So the Z effective is increasing, but yet there is a small discrepancy in the trend here. Okay. This is happening because of the poor shielding of electrons in gallium. Okay. So if it comes to aluminum and gallium here, right? So you can see that here we will have, suppose if you have, let's say, gallium here. Sorry, let me write down the configuration of gallium. Gallium up to 18 electrons, I'll write it from 18 electrons onwards. 18 electrons are up to argon. Then we have 4s2. Then we have 3d10, 3d10, and 4p1. Okay, 4p1. Correct? This is what you will have. 3d10 because gallium is 31. So 4p1 is what is the configuration. Now, notice this. I told you that when it comes to d orbital, they are very poorly shielding the outermost electron. If they are poorly shielding this outermost electron, that means the atom is attracted strongly to the nucleus. If it is getting strongly attracted to the nucleus, what happens to the size? Automatically, size will start shrinking. That means this electron, which is supposed to be here at this orbit, now it will start coming closer to the nucleus. Correct? Because d orbital electrons are not strongly shielding the outermost electron here. Okay. So you can see this is 4s2, 3d10, and 4p1. Okay. And that's the reason why gallium will have smaller size than aluminium, because in aluminium we do not have 3d electrons, but gallium has 3d electrons. And the same goes with thallium also. Thallium has 5d electrons. Because of the 5d electrons, again it will have poor shielding, and the 6p1 electron experiences more closeness inside. That's the reason indium and thallium has very comparable sizes. And this keeps going on group after group. But in other groups, what happens, the size is not something that it will dominate than the other upper element, but only in group 13 it will dominate. So therefore, boron towards thallium, this is how the size would vary. Everybody understood the exception of group 13? Of course, we can discuss about every other group here, but as much as our syllabus is concerned, in this topic, we will not have to go in detail about it. We have a separate chapter for every group. Okay, then we can discuss. Notice how the size is varying from D and F elements here. D and F D and F blocks. D orbitals and D block elements are categorized into three series of elements, right? One is 3D, 4D, and 5D series. If you analyze one series, that is more than enough because the similar thing follows in other series. Notice, if you go from scandium towards zinc, what is happening? For scandium towards chromium, the size is actually decreasing. Why? Because here Z effective value is dominant. Of course, sigma is increasing, but Z effective value is increasing slightly more. So therefore, if Z effective increases, size decreases. From chromium to manganese, there is a slight increase in the size, but from there, it will again start decreasing, but almost maintains a constant between iron, cobalt, and nickel. Hardly much difference, which means the increase in ZF and the increase in sigma value is almost significant. Correct? So, sorry, what I meant to say is any increase in sigma value here and here will compensate by the Z effective value. Therefore, you would almost see the Z effective similar value for iron, cobalt, and nickel. And lastly, copper to zinc, again the sigma value dominant and the size will start increasing. Okay. So this is a slightly different and observed. It is not completely decreasing. So it will decrease first, almost remains constant, and then increase towards zinc. And the same follows for 4D and 5D series as well. Okay. Next,
So,
if it comes to beta,
why is it different for MN?
why is it different for
MN?
manganese? Manganese would start losing its metallic nature because of its D5 configuration. D5 configuration is a very stable configuration, and D10 configuration is also very stable configuration. Correct? When you have this configuration elements, they will start losing out their metallic properties. Why? Because they will share less number of electrons in metallic bond. I will discuss in detail about what are metallic bonds. Then you will have a better picture of it. Okay. So due to that metallic bond nature, because the metallic bond nature is weaker in manganese and zinc, their size starts increasing. Okay.
Yeah, okay, sir.
Right. Next, if you compare the radius down the group, we expect there should be an increasing trend. So if you notice the third group element that includes scandium, yttrium, and lanthanum, the size is definitely increasing. And that's what we expect also. But if you go to the next element, that is titanium, zirconium, and hafnium, if you notice here, you would notice that the zirconium and hafnium has hardly any change in the size. In fact, दोनों का size almost same है. Why would this happen? Because the minute you enter hafnium, here just zirconium towards hafnium, in between there are 4f electrons. So 4f electrons are completely filled. And you know that f electrons are even weaker screening than d orbital. Correct? D orbital electrons are poor screening, and f electrons are even poorer screening electrons. That means they will give a very strong attraction to the nucleus, will give a very strong attraction to the outermost orbit. So that will start shrinking the size. So Z effective is high, right? Let me write on that. Z effective of hafnium is high due to poor shielding of F electrons, poor shielding of F electrons to the outermost electron. Guys, why am I so concerned about outermost electron? Because that itself will define the size. You know? The size of an atom is defined on the outermost electron. Correct? So to how far the outermost electron is spread. That's why we are always bothered about discussing outermost electron. Clear? So there is a term that is used for this effect, that's decrement of this size, that is known as lanthanoid contraction. This is called lanthanoid contraction. So it is due to this effect of lanthanoid contraction, hafnium size decreases and it almost becomes similar to that of zirconium. Okay. So titanium is less than zirconium, but zirconium is greater than hafnium. And the same follows the rest of the groups also. Vanadium is less than niobium, but niobium is same as tantalum. Okay. Chromium is less than molybdenum, but molybdenum is almost same as that of tungsten. And it follows group on group. Okay. So that means if we compare copper, silver, and gold, gold is almost same as that of silver. Got it? Done. I have written it here. What is lanthanoid contraction? So you can see in lanthanoids and actinides, there is a typical decrease in the size due to lanthanoid and actinoid contraction. If from left to right, always the size will decrease. Okay. That means if you take it from cerium towards lutetium, right, or thorium towards lawrencium, correct? In these cases, size decreases. Here also size decreases. Got it? And lastly, in case if you are removing the electrons from the outermost orbit and only keep d orbitals, that is when you have +2 oxidation state. That means scandium has +2, titanium has +2 charge, vanadium has +2, all of them. In that case, the trend is very simple. It decreases from left to right. Okay, ionic size will decrease from left to right. Oh, I wrote increasing. Sorry, this should be the opposite direction. So it should start decreasing from left to right. This way. This way. Okay. Got that? And same goes down the group also. If you remove that electrons from 4s electrons or 5s electrons or 6s electrons, then down the group the size will always increase. Last thing, this we have already learned that higher the positive charge, lesser the size. Higher the negative charge, larger the size. And that's why manganese +2 will have larger size than manganese +7. Okay. So guys, I hope you understood the characteristics of all the sizes here. Any doubt?
No, sir.
Right. Let's see the next important parameter which influences the periodic properties, that is ionization potential or ionization energy. Okay. See, the minimum energy that is required to remove the loosely bonded outermost electron from a ground state to an isolated gaseous state atom, that is called as ionization. What I meant, like you need to have a gaseous state atom, remove the loosely bonded outermost electron out of it, convert into a positive charge ion, then the energy required to do is called the ionization. If you are removing the first electron, you call it as the first ionization energy. If you remove the second electron, you call it as the second ionization energy, and so on. And we just learned that the minute you start getting more and more positive charge, the size will decrease. If the size decreases, it requires even more and more energy because it becomes harder and harder to remove the electron. So therefore, E1 will be less than E2, then less than E3, and so on up to En for any element. For any element, removing the first electron is less challenging as compared to that of second electron, third electron, and so on. Okay. So you can see size of the atom decreases every time you remove the electron, and this is how the size of the atom changes. And ionization is an endothermic change. That means energy is required here, and it is measured in electron volts per atom or kilojoules per mole. Okay. What are the factors that influence the ionic size now? Let's discuss that factor. What are the factors that influence it? Correct. The first factor that influences here, correct, when it comes to uh, ionization is the atomic size. So if the atomic size is larger, definitely ionic size will decrease. So we can say that, which implies ionization energy decreases down the group. It decreases down the group. So generally, I can say ionization energy of lithium is greater than sodium, greater than potassium, greater than rubidium, greater than cesium, and so on. The same goes even in the case of fluorine, chlorine, bromine, iodine, this way. So you most of the cases ionization always decreases down the group, okay, because the size is increasing, okay, and size also decreases from left to right. So we expect the size should also decrease from left to right, correct? I mean ionization should also increase from left to right, okay. So if you put off all those factors, first let me put the second factor and then I'll discuss that. Next one is effective nuclear charge, that is Z effective. So if the Z effective increases, size will automatically decrease and ionization will increase. Third factor is about screening factor. Screening factor, which is sigma. If sigma increases, ionization energy will decrease because poorer the, I mean, more the screening factor, more less will be the ionization. So therefore, Ns electrons, if it comes to Ns electrons, it is difficult to remove the electrons from here as compared to that of Np electrons as compared to that of Nd electrons when it comes to ionization energy. Okay. Next, fourth factor is principal quantum number. Principal quantum number. That is, if the n value increases, you are going away from the nucleus. If you go away from the nucleus, ionization decreases. So for n is equal to 1, sorry, if you take n is equal to 1, 2, 3, 4, then ionization for this first shell will be greater than ionization for the second shell, greater than third shell, greater than ionization of the fourth shell. The fifth factor is penetrating power. Penetrating power. That is, we learned that S has more penetrating power than P, D, and F. And if this penetrating power is more for a particular orbit, NS, NP, ND, and NF, I just told you that this is how the ionization factor will vary. Got it? The sixth factor, right, is about half-filled nature. Okay, before going that, let me take one example here. For example, suppose if I consider beryllium, beryllium is 1s2 and 2s2. This is the configuration of beryllium. While when it comes to boron, it is 1s2, 2s2, and 2p1. So this is the first electron in P and this is the last electron in S. That means you are trying to remove this electron and here you are trying to remove this electron. So we are talking about the ionization energy in the s orbital electron and ionization energy in the p orbital electron. So therefore, removing of the first electron for beryllium is more difficult than removing of the first electron from boron. Here you are removing from 2s, here you are removing for 2p. And the same follows even for magnesium also. That is, for magnesium, removing the first electron is more challenging than removing the first electron from aluminium. Okay. The next case is about half-filled and fulfilled. Half-filled and fulfilled stability. Half-filled and fulfilled stability. Okay. That is, if you have nitrogen, for example, I have 1s2, 2s2, and 2p3. So in the case of 2p3, if you have more number of unpaired electrons, we expect that is more exchange energy. More exchange energy. And more exchange energy implies more stability. And if this is more stable, it is difficult to remove the electron. So that's why removing electron from the first orbit will be challenging. So when it comes to oxygen, It has 1s2, 2s2, and 2p4. So in 2p4, if you notice, we have two electrons here, 1 and 1. Okay. Now it is the other way around. After after removing electron, then it will start becoming 3 electrons here, and now it has more exchange and it will become more stable, which means oxygen is ready to lose electron because losing electron will make it more stable. On the contrary, nitrogen does not want to lose electron, so it requires more energy in this case. So therefore we can say first ionization energy of nitrogen is greater than first ionization energy of oxygen. All good? The same follows for the next element also. First ionization of phosphorus is greater than first ionization of sulfur. Okay. It keeps going up to arsenic and antimony also. Okay, 1 second. So first ionization of arsenic is greater than first ionization of selenium. Correct. Now, if the first ionization varies this way, if you compare the second ionization, by the way, if you take the second ionization, now obviously oxygen has become half filled, so that will be very difficult to remove now. So the second ionization of oxygen will be greater. Here, phosphorus second ionization will be lesser than second ionization of sulfur, and second ionization of arsenic will be less than second ionization of selenium. Okay. So this is about the ionization, everybody. Done?
So can you explain the fifth point again?
Fifth point. The fifth point suggests that since if this is nucleus, you know that s electrons will be much closer as compared to that of p electrons. P electrons will be slightly far away. That is what we call it as penetrating power. So if an electron which is present in s orbital to remove and electron which is present in p orbital to remove, which one is easier? They removing
P.
electron from p orbital.
Yeah.
Correct. So here we require less amount of energy. That's why when you are releasing electron from p orbital in boron versus releasing s electron from beryllium, which will require more energy. Beryllium requires more energy. Okay,
Yeah, got it.
right. Now, lastly, check out what is the trend of ionization here. Okay, when it comes to ionization energy, if you go from left to right here, okay, so if you go from left to right here, you will notice that lithium is lesser than boron, lesser than beryllium, lesser than carbon, oxygen, nitrogen, fluorine, and neon. This is the trend which will follow. Where is the change that has been appeared? Beryllium and boron. We are expecting boron to be more, but beryllium is more. I just explain you the reason. We expected oxygen to be more, but nitrogen is the more form. That also expected. Okay, I just explained you why is that. Okay, and next down the group. Okay, so if you go down the group here, there is a regular trend only. So lithium, potassium, sodium, potassium, rubidium, and cesium. Okay. Where are the exceptions if you go down the group here? If you go, the exceptions where you will find here is ionization of gallium being greater than aluminum because the size is lesser here, and uh, hafnium is greater than zirconium, correct? And mercury is greater than cadmium. Gold is greater than silver, all because of lanthanoid contraction in these cases. Please check. Any doubt? See the next one. What are the applications of ionization here? See, metallic and non-metallic character depends on ionization. If the ionization energy is more, that means it is less metallic. It is more non-metallic character. And that's why you see, as you go from S towards P, ionization is increasing. The nature of the elements is more becoming non-metallic. But as you go down the groove, the ionization is decreasing. The nature of the elements is becoming more and more metallic. Okay. Reactivity. More is the ionization, less is the reactivity. Correct. So group 1 elements are highly reactive because it has very less ionization energy. Third, stability of oxidation state. Next, notice if two successive ionizations are compared and if they are greater than 16 electron volts, then the lower oxidation state is more stable. For instance, if you take sodium, okay, so if we compare the ionization energy of sodium, okay, got it. Let's say the first one is X1 here, the second one is X2 here. This is the ionization. And I told you that every time you try to make an ionization, it will always keep increasing. Got it? Okay, 1 second. Right. See the difference in the energy here. The difference in the energy, what has been found between these two is approximately 42.7 electron volts. In fact, the X value is 5.14 electron volts, while the X2, that is the second ionization value, is 47.2 electron volts. Okay. So approximately we have 42 electron volts difference that has been observed. But how much is the difference I'm expecting? 16. Of course, it is greater than that. If the second ionization is so high, which suggests that if after first ionization, getting this plus charge is very, very difficult. So now you tell me which one is more stable. Obviously, we can say Na plus is more stable as compared to that of Na2 plus. Is this point clear? Now notice when it comes to, same thing when it comes to magnesium. Okay. If you notice the magnesium part here, how much is the electron volt difference here? Got it? In the case of magnesium, the difference in the two successive ionization, if it is just less than 11, then the higher oxidation state is always more stable. Got it? So in the case of magnesium, the first value is 7.65 electron volts. The second one is 15 electron volts. The second one is 15 electron volts. Okay. So now you see the difference between these two here. So the amount of difference between these two is hardly 7 units. So which means since the first ionization and second ionization difference are lesser, the magnesium would prefer to stay more in +2 form rather than +1 form. That's the reason why Mg+2 is more stable than Mg+. Okay. Got it? Now, lastly, if it comes to aluminium, in the case of aluminium, if you compare the size, if you compare the electron volts here, the first ionization to remove the electron is 5.99, okay, almost 6. Al plus 3 is 18.83 and Al plus 3 is 28.45. Please notice the difference here. Between these two, there is a difference of almost 10 units, in fact, almost 11 units. So, like I said, if the difference is more than 11 units, then we can say the higher oxidation state is more stable. Okay. And between these two, the difference, if you notice, clear, between 6 and 18 here, the difference is almost 12 units here, correct? Approximately around 12 units. So in that case, you notice the amount of energy difference between these two is higher, correct? So it would prefer to stay more in +1 rather than +2. Is that point clear now? That's why the highest stability is for +3, then for +1, then for +2. Okay, these are all in electron volts per mole. Okay, electron volts per atom. Any doubt here, guys?
So do we need to know how did you calculate those EVs?
No, no, no. You don't need to know that. It is just to understand the trend. Okay. The values which I'm writing is just to help you out in terms of realizing how much is the difference. That's all. It's not like you have to mug up or anything. Correct? You just need to know how this order is. Okay. Done, everybody? Right. Okay. So we'll stop it here for today. So this is about the entire ionization